Hello everyone. So let's start with today's session. Welcome to the channel of DigiMento. Today we are going to discuss the subject algorithm. Okay, algorithms. So today we are going to discuss this in a very specific way. Okay, this is a quick revision for you all. So those who are preparing for 2025, this lecture is for them. Those who want a quick revision on algorithm. So here is the session for you all. Please watch till the end, subscribe, like, okay, and do watch the other videos as well where I have taken the short notes on data structure and C programming as well. Okay, so and if you have any doubt here in this, so do ask me. So let's get started with the class, everyone. So in algorithm, first we will discuss functions. Okay, so in the functions we have, first is logarithmic functions. So what is the example of logarithmic function? For example, log n. Okay, log n, these are logarithmic function. After that, the second is polynomial function. So in this we will say that it is denoted as n to the power x, where x is greater than equals to 0. So it can be n, it can be n square, it can be n cube, and so on. So n cube and so on. Okay, third we will be discussing, third is exponential function. Exponential function where the higher value of growth is there. Okay, higher value of growth is there. So exponential function is denoted as denoted as a to the power n, where a is greater than 1. Okay, so for example we can take 2 to the power n, 4 to the power n factorial, n to the power n, and so on. Got it, everyone? So these are all the functions. Right, now let's see the next one. So next one we will discuss about time complexity. So time complexity, here we can have best case, worst case. For smaller function are in order of bigger function. Bigger functions are omega of smaller functions, and the rate of growth of both is equal to the theta of each other. Okay, so smaller function is omega, bigger function is big O. Okay, everyone? Yes, so this is all the thing. Now let's see that the properties of log. Okay, properties of log are very important. Let's see the properties one by one. So how we will write log x to the power y? So it will be y log x. Second is log x into y will be written as log of x plus log of y. After that, third is log n will be written as log n. Okay, fourth is a log bx is written as x log b a, like this. Fifth is log kn is written as log n of k. Okay, whole power. Sixth is log by x by y can be written as log x minus log y. Seventh is log base b a can be written as 1 upon log a base b. Eighth is log b 1 by a can be written as minus of log b base b a. So these are all the properties. Okay, now let's talk about the notations. notations. So the very first is big O of O, big O, where f of n is big O of g of n. Okay, where function f of n is smaller than equals to c x g of n, and this, okay, this can be not x, okay, this only is just c, and this c can be any constant. Okay, second is big O, big omega. So this is nothing but f of n is omega of g of n. Okay, where f of n is greater than equals to c of g of n. Third is theta. Theta means is represented like this when f of n is theta of g of n. What this means that when f of n, we can write it as big O of g of n, and f of n also can be written as omega of g of n, then we will say that it is theta of g of n. Okay, when both the sides are same. Fourth one, small o. So small o means strictly bigger. F of n is small o of g of n. This means that g of n is strictly bigger than f of n. Okay, g of n is strictly bigger than f of n. So this is, so here you can see that equals to symbols are there, but here it is not, no equals to, it is strictly greater. Same for small omega. Small omega, so here also strictly smaller. F of n is small omega of g of n. Okay, so it's like this. Now f of n is small, like f of n is greater than g of n, like this it is. Alright everyone, now let's see some summarization, not summarization, summation series. That is also very very important. So let's see that. Summation series. The very first is k is starting from 1 till n, which is 1 plus 2 plus till n, so which is equals to n into n plus 1 by 2. Second is summation of k is equals to 0 till n and x to the power k, so which is 1 plus x square till xn, so which is x n plus 1 minus 1 x minus 1, and here we will say that x is not equals to 1 because it will be equals to 1, so it will be 0 and the series will not be possible, so that is why x should not be equals to 1. Third is summation of k equals to 1 till n, where 1 by k, so it is 1 plus 2 plus so on. Okay, so on till 1 by n, so this is approximately equals to log n. Okay, now let's discuss some geometric sum formula. Okay, so that is very important. Geometric sum formula. First is if r equals to 1, then s of n is equals to n into a. So this is the first term. After that, second is if r smaller than 1, so this is s of n a 1 minus r n 1 minus r. Third is if r is greater than 1 and this r is common ratio. Okay, where s of n is equals to a r to the power n minus 1 r minus 1. So any doubt here in this? Any doubt in this? So if r equals to 1, then this is the formula. And for infinite, so this is for finite terms. This formula, you should note, this is for finite terms, okay? And for infinite terms, it's if r smaller than equals to 1, so s of infinity equals to a 1 minus r. Okay, now let's write some dominance relation. So first will come constant. Okay, after that logarithms, after that polynomial, after that exponential. Okay, so if I take one example, so it will be like this. Example 10, here if log n is there, so it's greater than 10. If root n is there, it's greater than log n. After that n, after that n log n, it's greater than n square. Then 2 to the power n. After that, it's greater than n factorial and it's greater than n to the power n. Like this it will be. Okay. Now let's see f of n if this is 1, I equals to 1 to n, so the value will be n and this will be big O of n. Okay. Second is f of n I equals to 1 to n and this is n, so what it will be? N square, right? So I equals to 1 to n 1 and this will be big O of n square. And the third is f of n if I equals to 1 till n I, so this is n into n plus 1 by 2 and this is big O of n square. Fourth is f of n equals to I equals to 1 n I square, this will be n into n plus 1 2n plus 1 by 6, so this will be n cube. Okay. Now fifth one is f of n I equals to 1 n I cube and this will be n plus 1 by 2 and this is a square, so this is big O of n4. So now this is f of n where I equals to 1 till n 2i, so this will be 2 n plus 1 minus 2, so this will be big O of 2n, 2 to the power n. Okay. Seventh is f of n is equals to I equals to 1 till n, and this is 1 by 2 to the power I. So this will be 1 minus 1 n, and this will be big O of 1. Okay. 8th is f of n equals to I equals to 1 till n I into 1 into 2 to the power I. This will be n plus 1. This will be n minus 1 2 to the power n plus 1 plus 2. So this will be big O of 2 to the power n. Okay. 9th will be f of n equals to, now if there is a pi, okay, I equals to 1 till n, so this will be big O of 1. Okay, and always remember the 10th point, very important. Log of n factorial is equals to theta of n log n. Okay everyone, so this is one of the important thing. After that, let's see some general properties of big O notation. Okay, so let's see that. I hope this all things are clear to you all. So Vinita, today's topic is algorithm. So all we are discussing is algorithm today. Okay, in a very short way, so that all the revision should be done. Now let's see the next one. So general properties of big O notation. Okay, general properties of big O notation. The very first is if d of n is big O of f of n is big O of f of n, then a into d of n is big O of f of n, where a is greater than 0. Okay. Second is if d of n is big O of f of n and e of n is big O of g of n, then we can say that d of so this is m, right? So d of n plus e of n plus e of n is big O of f of n plus g of n. Okay, so this is the case. After that, third is if d of n is big O of f of n and e of n is big O of g of n, then d of n into e of n, so is big O of f of n into g of n, like this. Okay, it is like this. After that, let's see now reflexive, symmetric and transitive properties. So big O omega theta small omega, and this is, here it will be reflexive, symmetric, transitive. So it is what basically? So this is reflexive omega theta, but it is not small omega and small o. Symmetric is none, only theta is there. After that this is not there. Transitive, all are transitive. Okay, so the tick will go to all are transitive. So this is the table which you should remember. Now let's discuss some common recurrence relation. Okay, some common one. So let's discuss them. Common recurrence relations. Very first is T of n equals to a plus T of n minus 1 plus b, where n is greater than 1. Okay, and a is equals to, a is greater than 0, b is greater than 0. That means they are constant. So this will have theta of n. Okay, second is T of n, where a plus T n minus 1 plus n is there, then this is theta of n square. After that, third is T of n is equals to a plus T n minus 1 plus n by 1 by n, where n is greater than 1. So this is theta of 1. Okay, so this you can directly remember these properties. These properties you can directly remember. Okay, now let's see the next one. So the fourth one is T of n equals to 2t n minus 1 plus d, and where n is greater than 1. So it will be theta of 2 to the power n. Alright, now let's see the fifth one. T of n equals to a plus t n root, where n is greater than 2. So this will be big O of log n. Sixth is T of n is equals to a plus 2t under root n plus b, where n is greater than 2. So this is big O of log n. Seventh is T of n is equals to root n into t, like this, plus 1. So this is, n is greater than 2. So this is big O of n log n. And I guess this was the question in GATE 2024. This was the direct question in GATE 2024. This exactly. Okay, and what was the answer? So if you remember the answer, you would have directly ticked the answer on the screen by seeing the option itself. But if not, then you have to solve it by taking n 1 by 2, t n 1 by 2 plus 1. After that, using substitution method. So sometimes this is also very important to remember. Okay, after that, eighth is, and these are some common things which I am telling. So this is 2t n by 2 plus d, and this d is nothing but constant. Okay, so n is greater than 1. So this is big O of n. Ninth is t n by 2 plus d, where n is greater than 1. So this is nothing but big O of log n. Big O of log n. So it's better to know prior, right? If you know this in prior, so it's easy to mark there and there itself. Okay, let's see further. 10th is, so by Master's theorem also you can solve, or directly you can just remember. But Master's theorem will work on some specific formation, some specific format which it has. So big O of n cube, and 11th will be T of n is equals to 2t n by 2 plus n log n, and this will be big O of n log square n, like this. Now let's see some loop complexities. Loop complexities. So let's suppose we have for I is starting from 1, I is smaller than equals to n, I equals to I plus a, and this will be n by a. This will always be n by a. For I equals to 1, I smaller than equals to n, and this is I equals to I into a, then this will be log an. Alright everyone, I hope there is no doubt. Now let's discuss master's method for solving such recurrence problem. So there are three properties, right? After that we will see divide and conquer problems. So let's discuss master's theorem now. Master's method, okay, for recurrence relation. So what is the format? Tn is t n by b plus f of n, where a is greater than equals to 1, b is greater than equals to 1, and these are constant, and f of n is positive. Okay, so the first condition is that if f of n is big O of n log b base a minus this this symbol is constant, okay, for some this notation greater than 0, then what happens? T of n is theta of n log ba. So in short, if I tell master's theorem, okay, so it's like f of n. So if f of n is greater, or if this is greater, so if this is greater, just directly write this, and if f of n is greater, directly write f of n. Okay. Now the second property is for the equal one. So it's like if f of n is theta of n log base ba log kn for some k such that first is a, k is greater than equals to 0, then what we have to apply? T of n. So for the change, let's write p of n, okay, p of n equals to theta of n log base b a into log k plus 1 n, okay, and b is k smaller than 0, so then let's use t of n equals to theta of n log b base a into log n. It will be like this, okay. And the third one is if f of n is equals to omega of n log base b a plus e, and this is greater than 0, and a of f n by b. So this is the exceptional condition, okay. This you don't need to check. If this is satisfied, this always gets satisfied, so don't worry about this. Then it will be direct t of n theta of fn, okay. So theta of fn. So whichever is greater, that you have to write theta of that. So here in this case fn is greater, so I have written theta of fn. Here in this case, this n log n base b is greater, so I have written like this. So it depends which is greater, and if it is equal, then that is the second case of master's theorem. Alright. Now let's see divide and conquer problem. So one by one we will see divide and conquer problem. After that we will see greedy method problem. So the next topic is divide and conquer problems. The very first is max min problem, which is t of n equals to 2t n by 2 plus 2, where n is greater than 2, and this is like t of n equals to 3n 2 minus 2, so big O of n, and the space complexity here will be big O of log n. Okay, and this is for all cases. Okay, or let's not write this specific. So this is max mean. Okay, now let's talk about binary search. So for binary search, it is t of n is equals to 2 n minus n by 2 plus a n greater than 1. Okay, so the max number of comparisons is log n, where n is number of elements. Okay, n is number of element. So time complexity will be big O of log 2 base n. Space complexity will be big O of log n. And this is for recursive. Okay, this is for recursive. Everyone. Now let's see for merge sort now. Third is merge sort. So t of n is equals to 2t n by 2 plus b of n, where n is greater than 1, b is greater than 0. So the time complexity will be theta of n log n, and space complexity will be big O of n. Okay, and number of comparisons to merge sorted array of size m and n. So what is the thing? Minimum of m comma n smaller than equals to number of comparisons smaller than equals to n plus m minus 1. Okay, and number of recursive call is equals to 2n minus 1. Right, now let's discuss for the quick sort. I hope that merge sort is absolutely clear. Okay, I hope there is no doubt here in this. Now let's discuss quick sort. Quick sort. So t of n is big O of n plus 2t n by 2, and this will be big O of n log n. Okay, so if elements are in ascending or descending order, then t of n is equals to big O of n plus t n minus 1. So which is big O of n square, and this is the worst case. So if in the sorted array, if you will try to apply quick sort, then it will give you the worst case of n square. Okay, so space complexity. So best case is big O of log n, and worst is big O of n. Okay. Now the fifth is matrix multiplication. Matrix multiplication is T of n equals to 8t n by 2 plus bn square, where n is greater than 2, b is greater than 0, then time complexity is big O of n cube and space complexity is big O of log n. Alright. And by Stressen's method, this is little bit improvised. Okay, matrix multiplication. So, Stressen's method, the time complexity reduced to t of n, which n 7t n by 2 plus bn square, where n is greater than 2, b is greater than 0. Okay, and t of n smaller than n 2.81. And the space complexity is log n plus n square, so which is big O of n square. Now the sixth one is, let's talk about long integer multiplication. Long integer multiplication. So this is t of n equals to 4t n by 2 plus bn. N is greater than 1, b is greater than 0. So the time complexity is big O of n square and space complexity is big O of log n, like this. Okay everyone, now let's discuss greedy method problems. Greedy method problems. The very first is knapsack and the time complexity is big O of, so let me write big O, it's looking like small o, big O of n log n. Okay. Second is job sequencing with deadline. So this will take time complexity of big O of n square. Okay. The third is optimal merge pattern. Merge pattern. So time complexity for that is big O of n log n and space complexity of big O of n. Okay. Now let's see Hoffman coding. Okay. Fourth is Hoffman coding. So it is an application of optimal merge pattern and Hoffman tree is constructed with starting from leaf node with character having lowest possibility. Like this. Now let's talk about minimum cost spanning tree. Okay. Fifth is minimum cost spanning tree. So the very first comes here, for that is Prince algorithm. Okay. So here the time complexity is big O of E plus V log V. So E is for edges, V is for vertex. So this is using Fibonacci series. Fibonacci heap we can say. And big O of E log V, this is using binary heap. Okay. Now using sorted array and adjacency list, Prince algorithm, time complexity is big O of edge into vertex. Now let's talk about Christian's algorithm. Okay. Kruskal's algorithm. So we have to sort the edge according to the weight, and then without creating a cycle we have to go to the MST, right? So the time complexity for this is big O of E log E, and if H sorted, then big O of E plus V will be the case. Now let's talk about Dijkstra. Okay, Dijkstra algorithm. So see, let's see the time complexity, how it will be there. So you all know that this is a single source shortest path. Okay, I'm writing. This is for single source shortest path. Very first is mean heap and adjacency list. So the time complexity is big O of E plus V log V. Second is adjacency matrix and mean heap. So this is big O of V square plus E log V. Third is adjacency list and unsorted array, which is big O of V square. Fourth is adjacency list and sorted doubly linked list. So this is big O of EV. Okay, E means edge, V means vertex. Okay, everyone. Now let's talk about dynamic programming. Okay, let's see the topic of dynamic programming now. So dynamic programming, the very first is Fibonacci series. Fibonacci series, where the time complexity is big O of n, space complexity is big O of n. Okay. Second is Floyd-Warshal's algorithm, where A of ij is equals to minimum of A of ij, where A of I k plus A of k j, right? Now the fourth one is knapsack 01 knapsack problem. 01 knapsack problems, time complexity is big O of n into m and space complexity is big O of n into m. Okay. Fifth is longest common sequence, subsequence. So time complexity is big O of m into n and space complexity is also big O of n into m. Okay. Now let's see matrix chain product. Okay. Matrix chain product. So time complexity is big O of n cube, space complexity is big O of n square. Seventh is sum of subsets. So time complexity is big O of n into m, space complexity is big O of n into m. Okay. Now let's note some few points for this. Note points. The very first is Dijkstra always wait for graph having positive edges. Okay. Dijkstra always is for, okay, like this. Second is if graph have negative edge and no negative weight cycle, Dijkstra algo may not work. May or may not work. Okay. So the third point is Bellman-Ford algorithm. So always works if graph have negative weight h, okay, but not negative weight cycle. But not negative weight cycle. Okay. I hope the point is clear. Let's see now the fourth one. If graph has negative weight cycle, so reachable from source to destination, then no algorithm works. Okay, in this case no algorithm works. Fifth is time complexity of Bellman-Ford big O of v into e. Okay, if e equals to v square when we have complete graph. So if complete graph is there, what will be the time complexity? Then it will be big O of v cube, right? So this is very important thing which you should note. Right. Now let's see graph traversal. Graph traversals. First is depth first search, second is breadth first search, okay? And time complexity of both depth first search and breadth first search depends upon whether it is adjacent matrix, so it will be big O of n square, and if it is adjacency list, then it is big O of n plus e. Okay, like this it depends. Now let's talk about some DFS leads to following edges. Okay, so the very first is tree edge. So what is tree edge? Part of DFS spanning tree. Second is forward edge. So forward edge means node to its non-child descendant in spanning tree. Third is back edge, which is node to its ancestor. Fourth is cross edge. So edge between two nodes such that they do not have ancestor and a descendant relationship. Okay, so few points you can note that both DFS and BFS can be edges. Okay, presence of cycle. Okay, if you detect presence of cycle, so as well as to check if graph is connected or not. So what is the purpose of DFS and BFS? To check, to detect cycle and to see cycle is there, so the graph is connected or not, and both DFS and BFS can be checked if two vertices are connected or not. DFS is used to determine connected, strongly connected, biconnected, okay, points, and a graph is said to be biconnected if does not contain articulation point, which is articulation point like this. So if this link will break, so this and this will be two different objects and it is linking. So this is the articulation point. Alright everyone. Now the next topic is sorting algorithm. Sorting algorithm. So here algos are there. Here best case, average case, worst case, okay, stable and in place. Now if we talk about quick sort, so best case is n log n, average case is n log n, and worst case is n square. This is not stable but in place. If we talk about merge sort, so best case is n log n, average case is n log n, worst case is n log n. Okay, this is stable but not in place. After that, heap sort. So this is big O of n log n, or theta also we can write. Okay, let's write this theta. We can directly say theta, theta of n log n and theta of n log n as well here. But this is not stable but in place. After that, bubble sort. So bubble sort is nothing but theta of n square and theta of n square. So this is both stable and in place. After that, selection sort, theta of n square, theta of n square, theta of n square. So this is not stable but in place. After that, insertion sort. So insertion sort is theta of n square and theta of n square. This is both stable and in place. Okay, now the topic which is left are binary search, AVL tree, heap. Okay, only these are the topics left. Otherwise, we have covered it all for the algorithm, whichever is needed. So this directly you can remember, everyone. Now for binary search, so this is BST, I am discussing binary search tree. So the tree in which every node satisfies, okay, so all the keys in left subtree are smaller than the node and the keys on the right subtree are greater than the node. And here insertion, deletion and search, all this takes average of big O of log n, and the worst case is big O of n when skewed BST is there. Skewed BST is there. So you all know BST, this is the root. Everything here is smaller and here everything is greater than root or equals to, like this. So this is BST. Okay. So tomorrow we will be discussing AVL tree, heap, and yes, and the algo will get finished. So tomorrow one of the subject again we will discuss. Right everyone? So till then what you can do, you can just see the other videos as well where I have discussed everything in short way. So it's a quick revision for you all. Okay everyone, so it's a quick revision. You can take most advantage of this list. So thank you so much. See you.